They can form new phases of matter that both challenge conventional physics understanding and provide living organisms the ability to perform amazing feats. So please join me in welcoming Joshua for tonight's Science on Hudson lecture.
All right. You know the introduction will be okay when your father is doing it. Excellent. So yeah, I'm Josh. I'm an experimental biophysicist, which means that I'm an experimental physicist, but I like to play with living things. We do lots of things on all scales. What I'm going to tell you about today is only partly my work. It's the work of many people around the world, but I think it's a subject that's quite interesting. So let me start. How many of you were here for one of the last couple of these lectures? Anyone? Okay. Where you learned about, fundamental particles, something about this dark matter thing. Okay. And let me just tell you, in your everyday life, none of you have ever cared about any of this, right? Like whether or not the atom is made up of 3 little parts or 2 little parts, like, I mean, really? No, right? Okay, but what you do care about, I mean, in fact, you don't even really know about molecules in your everyday experience. You know they're there, but you don't know, it's like, oh man, that molecule was, that really hurt or something. Like that doesn't happen. Why? Because there are way too many of them for you to be paying attention to each one individually. Okay, the world that you experience every day, this solid stuff, the liquid stuff inside here, has these properties because there are huge numbers of molecules, something we call Avogadro's number, which is 10 to the 23rd. So that's 1 with 23 zeros after it. That's a lot. Okay, and when you average over all of that, you just don't care about each individually anymore. In fact, you can just provably say that there's no way you could even try to care. Like if you wanted to write down all the equations for every molecule in this bottle, you just could not do it. Okay. But you also know that water is like a material that you understand stuff about. And the wood is a material you understand stuff about. Okay. So there's something about averaging over lots of molecules that brings out these universal or common phenomena that we understand as the material world around us. Okay, this is a subject called statistical mechanics, statistical physics, thermodynamics. All these things are sort of wrapped up. Okay, and it's the physics of real things. Okay, so you probably know about these 3 phases of matter. Okay, like you went to school one day and they told you there are 3 phases of matter, and you repeated it back, something like this. Okay, and there are solids, right, which are sort of hard and rigid, and they told you there were liquids, and these had to do with like pouring stuff, and like if you're in the swimming pool and you try to move your hand really fast, it's hard, it takes work, but if you try to move your hand slowly, it's easy. Okay, that's a funny thing. So that's something to do with the way the liquid responds to you. Okay, and then there are these gases, and they're very amorphous, and they do all this kind of thing. Okay, and so great. So you learned about this one day, and there was a quiz, and you had to write down 3 phases of matter, and that was awesome. Okay, but then maybe you learned about something about why it's like this. Okay, and so these are some, creative animations for things. So a solid, this is something like ice. These are something like water molecules. A solid is made of molecules that are bound together, usually in a semi-regular kind of an arrangement, like a lattice, like this, although that doesn't have to be true. But those bonds are very strong, and they're not very dynamic. They're just kind of stuck there. So the molecules are stuck there in some particular arrangement, and if you push on one of them, it pushes on all of them kind of together. So it stays together as one solid object, okay? Now, a liquid is sort of one object, right? Like the bits of water are stuck to the other bits of water. They're not going all flying around, okay? But if you push on one bit of water, one molecule or a set of molecules, they can slide past other water molecules. And that's what makes something a liquid. So this is a material where all the molecules are bound to other molecules, but those bonds are dynamic. I switch who I'm bound to actually very quickly. So all the time, the little molecules that you can't see because you don't really care about them in this water, they're exchanging neighbors all the time and exchanging bonds. I'm bonded to you, I'm bonded to you, I'm bonded to you, and then I go back and forth. And that's what makes a liquid. So that if I push on you, because those bonds are rearranging so quickly, you're happy to go bond with the person behind you and the person behind you, and you'll flow. Okay, and that's how we'll get flow. And how easy it is and how that time scale for bonding and how strong those bonds are, that gives rise to something called viscosity, which is basically how hard it is to make something flow. Is it kind of a thick fluid or a thin fluid is the language you might want to use. Okay, and then a gas is a collection of molecules that just don't really interact with each other very much at all. They're really moving too fast almost for the bonding with other molecules to matter much, and so they just are like wigging all around. So the air you're breathing right now, those particles of oxygen and nitrogen are basically not interacting much with the other particles of oxygen and nitrogen, and then you inhale them, and you can bind them to stuff in your lungs, and that's a good thing. If there's not enough of it, that's a bad thing. Okay, very good. So you learn about these things. Now, you also know, you probably didn't learn this in class because you have to take a few extra classes for this, but you know inherently that these phases can interact with each other in interesting ways. So what is that? Oil and vinegar. Very good. So first off, anyone, you should ask me questions. Like, I'm used to teaching a classroom, and if my students ask me no questions, I get very worried that they're buying something on Amazon and not paying any attention to me. So feel free to raise your hand. I can see all of you. It's dark, but I can see all of you. Yes. We will get to something that's like peanut butter, and then we'll come back to it. Okay? Yeah, well, peanut butter is a liquid, but it's a special kind of liquid. It's sort of solid-like and liquid-like. Yes. No. Not in this talk. It just doesn't get there. Okay, great. So this is oil and vinegar, right? Oil and water, basically. I mean, you don't make your salad dressing with water because you want the acidity, but you could make it with oil and water, and you make something called an emulsion, either by shaking or mixing, and you've done this before, and maybe there's a machine for this. And so this is basically tiny oil droplets suspended in water, is what this thing is, and that makes it kind of creamy because those little droplets are yummy and all that sort of stuff. But what happens to this if you let it sit? It separates, right? And the oil comes to the top because this olive oil is lighter than water. Not all oils are, but olive oil is. Okay, and it flows to the top. Okay, does anyone know what this phenomena is called? The thing that drives this separation? It's called hydrophobicity. Okay, oil is, we call it hydrophobic, meaning it doesn't like water. Okay, this is actually a really deceiving term, and I like to get my undergrads with this all the time. So if oil does not like water, I have the following experiment for you. The experiment that initially measured how big a molecule was did the following thing long time ago. You go to a lake, you drop some oil on it, and that oil spreads out until it is literally one molecule thick. And you can use this to calculate things like the number of molecules and the thickness of a molecule, all this sort of stuff, because you know the volume you started with, you know this area, you divide those two, you get a thickness. That's the size of a molecule. So if it does that, that implies oil really, really likes water, right? Otherwise, it would stay as a ball. It doesn't stay as a ball. It spreads out as much as it possibly can. It maximizes as much contact as it can with the water. So it loves the water. Why do we call it hydrophobic? It must love the water. The answer is that water loves itself much more. Okay, the water molecules bound to each other through the hydrogen bonds that they use are way stronger than the bonds you get from oil to water, but those are also stronger than the oil-oil bonds. So you have this sort of this hierarchy. Okay, so anyway, but regardless, oil wants to phase separate because the water loves itself too much. It's narcissistic material. Okay, and so we have this phenomena of liquid phase separation, and we're going to see that in future content. Okay, here is a solid called the Eiffel Tower. Does anyone know why the Eiffel Tower is shaped this way? Take a guess. Stability. The Eiffel Tower was the first tower to be 300 meters tall, the first human-made object that was that tall. And when Gustav Eiffel and the other engineers were designing this, they knew, well, the little bit on the top, can you see something here? So this little bit here on the top, that only has to support the weight of this. That's not so much. This stuff on the bottom has to support the weight of everything above it. So the bottom needs to be stronger. You need more material there. And the Eiffel Tower is actually built in such a way that basically every bit of steel has the same amount of mechanical stress on it everywhere in the structure. And so you have more of it in the bottom because there's going to be more total stress. Okay, and actually, they basically did this empirically, but then a mathematician in Berkeley a few decades ago calculated that this is essentially the right answer, even if you could solve it on a computer they didn't have in the 80s or whatever it is. Okay, so this is a special structure. We're going to keep that in mind too for some other things that we're going to see. Okay, so you're driving in the rain, and your windshield wipers break, and you didn't buy this funny stuff called Rain-X in the hardware store, and this is what happens. Okay, and this is an interesting phenomenon. The water here sort of likes to bind to the glass, but sort of doesn't like to bind to the glass. So it's staying as droplets, but not complete droplets. It's also what we call wetted, sort of bound to the glass. Okay? If you put Rain-X on, the water does not like to bind to the Rain-X. And so the water droplets form very round droplets that aren't bound to the glass, and they fall down via gravity and roll down. You wouldn't see it anymore. Okay, same kind of thing with a raincoat. If you have a new raincoat that has this waxy stuff or Gore-Texy stuff or something on it that doesn't like water or water doesn't like, and so it'll make these things and they'll roll off. As your raincoat gets older, this stuff kind of disintegrates or dissolves. I actually don't know what happens to this stuff, but the water then doesn't do that and it gets absorbed by your material and you're a sad, sad person. Okay, so we have this idea that liquids can be on solid surfaces and either wet them or de-wet from them, form droplets in different amounts. And that kind of has maybe something to do with how much you like the surface or don't like the surface, something like that. Okay. You know that if I take metal and I make it very hot, it becomes a liquid, right? Mostly you don't think of metals this way because everyday temperatures, most of them are not liquids. Some are. Mercury, which you're not allowed to have anymore, but looking in the audience, many of you have experienced mercury thermometers. Okay, I won't. Yeah, good. So this is some sort of liquid metal. Okay, but it's going to start doing something that I would say your normal liquids that you experience every day in your lives do not do. So these are aggregating. You could imagine that this would be possible if they're somehow magnetic and stuff. But then this is going to start. Well, he's not made of metal. But this metal does something, this liquid does something very weird. Definitely not what you're used to seeing from liquids in your everyday life, right? It becomes the Terminator. And, it's sad. I show this to the undergrads and they have no idea, like which makes me very sad because, this was a fundamental part of my childhood. So, okay, very good. Anyway, so that is a weird material, yes? That did something you're not used to. It seemed to have ideas of its own. It seemed to have directions it liked. Like if I drop water on the ground, it kind of just goes out. And assuming the ground is flat, it doesn't go anywhere in particular. This liquid decided to go over there. Okay, that is weird. It shows a direction. We like to think that the laws of physics don't have any directions in them, right? Like if I juggle this way and I juggle this way, it should kind of be the same. In fact, if I'm on a train that's moving very smoothly and I juggle, it's also the same. That's weird. I mean, it is weird. It's true, but it's weird, Anyway, so I'm going to put two equations in this entire talk. They're coming up. You're not supposed to read them. We're talking about the physics of stuff, this continuum thing. And this is the equation. Don't worry about what it means. It's called the Navier-Stokes equation. It's from the 1800s. It is the equation for essentially all fluids and gases and solids and stuff in terms of the way they respond to being pushed on and stretched and stuff like that. Okay? Now, these are regular materials. What if I had a material where the individual molecules, maybe I develop magic molecules, or maybe what I do is take a group of living things and I have so many of them, I can treat them as a material. Okay, so like if I had many, many of you and I made you stampede over there and I went to outer space and I kind of squinted, you would look like some sort of funny liquidy thing. And that's what we're going to talk about. When you try to write down this equation for that kind of system, you basically have to throw out all of these nice notions about how there's not allowed to be like special directions. Okay. One of the reasons that this equation is so simple, I mean, look, this is an equation of everything. I basically just told you, and it has like a few letters in it, right? The reason it's so simple is because there's all these rules that just have to be true because you're not allowed to have weird directions and weird speeds, just weird stuff. And so you're kind of limited in what you can do. If I make a material that doesn't have these properties, I get a very similar equation. Like there are sort of similar looking things here, but I have many more parts to it. And the reason I have many more parts to it is because I don't have these concepts of symmetries and everything has to be the same in all directions and stuff like that. I need many more parts to the math to make this work. And what this does is you need many more parts. You get many more different kinds of solutions then to this sort of equation. Now, this is actually very new. It's from 1998. It was developed in thinking about bird flocks at IBM Watson here in Yorktown Heights by John Toner and Yu Hai Tu. So this is really new stuff. So the things that we're going to be talking about, the motivation, certainly for me, comes from understanding living organisms. But what's been really interesting and really cool is that by studying the living organisms, we've realized that those organisms know more physics than us, and they can teach us new areas of physics that then we work on as physicists. And we realize there's this whole other branch of materials that could exist that are what we call active. Or you might say they're out of equilibrium if that word means something to you, but it doesn't matter. They're active. Normal materials are passive. Okay? There's dynamics. The molecules are moving. This has to do with something called temperature, right? Like, you know what hot and cold is. What hot and cold really is how fast molecules are moving on, which is kind of funny. In these fluids, it is not the temperature that moves things around. It's the fact that, you know, the birds are trying to go somewhere, or the cells are trying to go somewhere. Okay? Molecules moving around because of temperature move around randomly. That's like sort of, you know, from on high, that is the postulate. It's all random. And that's where everything comes from. Okay. Here, you have to throw out that randomness, and you can get many more interesting things. So if you look at the solutions to this equation, no more equations, you'll be happy. Okay, good. You get all the normal things, okay, but you get new solutions. For example, you guys have lots of Canada geese here. Sometimes you look in the sky, and they are flying, not as the bird flock that we'll talk about later, but in this like V-shaped thing. And that V-shaped thing is a solid. The birds are not exchanging positions. What happens in a liquid? Like eventually all the things are sort of mixing up on some time scale, something like this, even though it stays as a cohesive whole. In a solid, the particles do not change their relative positions relative to each other. Same thing in this true as this bird flock. This is a solid object, except now instead of sitting somewhere, it moves in space. So this is a moving solid solution to those equations. You can get a moving liquid solution. So this is a fish school. I won't be talking much about fish, but we partly work on fish. And so this is a bunch of things. They are clearly like a cohesive whole. Okay. And in fact, they do have some ordering to them, but they are allowed to change orientation. And they do, if you move one of the boundaries, it's almost like pushing on it, and that will apply a shear, and they will flow relative to each other. So this is like a moving liquid. And then bird flocks, this is a gigantic bird flock, look like a gas. If you look in detail, the birds are changing positions. It looks much more gas-like. There's a little bit of adhesion, right? Because it's not just flying all apart, but it's almost that way. So this is more of a moving gas kind of a solution. Okay, so if I allow my particles to have motion that is not just random because it's driven thermally, I get new solutions to the physics equation. Okay. There's another part of biological active matter that we want to consider, and that's that the particles, if we're thinking of the birds as a particle in a flock, well, they're not even just moving on their own volition, but they can like see the world around them and make complex decisions and stuff like that. And so now you can endow your particles with lots of intelligence and lots of things, and that could get even more solutions. And we'll see a little bit of that as we go forward. Mostly it'll be quite statistical, but some of this will come out. Okay, so we come to the first story I want to talk about, and this is going to be about collections of fire ants. This is mostly work done from my friend David Hu, who's at Georgia Tech. He has this wonderful popular science book I invite you to buy about how to walk on water and climb up walls, about animal movements, and how sort of the world of robotics has been improved, and what people have learned by studying how animals move in order to build better robots. And the whole story is going to be about this fire ant. So, fire ants are kind of scary, but if you go to the south, there's a lot of fire ants. And they live in the ground. They make these nests, sometimes very large nests, sometimes small nests. They'll bite you, so don't mess with them. They're actually really insidious. Like, they grab onto you with their mandibles, with their teeth, and then their stingers in the back, and they just start stinging you. And they're stuck to you, and you can't get them off, and they're mean. Okay, but when it rains, okay, the water fills the nest, and that's bad for them. So they need to emerge from the nest. Okay, and then if it really rains, in the south, not only are there fire ants, but there's really a lot of rain sometimes, and the whole thing floods. Okay, and so now they basically run out of dry land. And what they're going to do is they're going to form a raft that lives on top of the water. Okay, and as we're going to see, this is a liquid and has liquid properties in all these things. Okay, so let's try to figure out how it forms this and what this does for them and how they use it. Okay, so the first thing is that ants are hydrophobic. So if you take a fire ant and you stick a droplet of water on top of that, right, it doesn't spread over it, it forms a little drop. And if you take a raft of these guys and you put them on water, it will push the water down. Okay, so this is how they float. This is how they can move around. This is how they keep themselves from like sinking and dying inside the water. Like if I put a whole bunch of you, I said, oh, hold hands, I'm gonna drop you in the ocean, you go down, right? These guys don't because they're hydrophobic. Okay, it's a cool experiment. I like. You don't usually think I can push on the surface of water. Okay, so how do they get together in the first place? Well, if they're in the water, the way they originally find each other is a really cool piece of physics called the Cheerios effect. I'm sure many of you have eaten Cheerios or had kids who eat Cheerios, something like that. And then you get things like this. Yeah? Yeah. Did you ever wonder why? I mean, it wasn't until like the 90s that anyone actually like studied this. Okay? And what happens is the Cheerios push on the milk and they create a curvature of the surface because they're basically bound to the surface. And those curved surfaces of liquids interact with each other because it costs energy to curve a surface. And if I put two Cheerios together, I have to spend less energy because I have less curved surface because it's only on the edge that it's curved. And so that applies essentially a force that makes them want to group together in something that literally the physicists call the Cheerios effect. Okay, it's a surface tension-based effect if you want to think about fluids. Okay, so this is what happens with the fire ants. They displace the water. You can see it. That makes this curved surface. The curved surface from ant A interacts with the curved surface from ant B and causes them to want to sort of clump up. Okay, so if they're in the liquid, they will naturally coarsen like this. Okay, once they're like that, they bind to each other through dynamic bonds. Remember, in the water, we had these molecules, but they were bonding and bonding and bonding and bonding, and that's how I could make a fluid that I could move things around, a liquid. Okay, so their legs are full of these tiny little hairs, and if two legs kind of touch each other, they basically get kind of meshed up, and that forms a little bond. It's kind of like Velcro. Maybe easier to rip off, but something like the concept of Velcro. Or, if you walk in the forest, there are those plants that make something like that, and they're like super annoying, right? I mean, it's like that. Okay, and so this allows them to make dynamic bonds. You can see they can hang on to each other. They can do all sorts of stuff. And so as they're moving around within this group of cells, they can change neighbors. They grab this one, they grab this one without having to like grab. They basically just touch them and they'll stick. So you can study these groups. So here's like a big jumble of ants, and you can put it in a CT scanner and go through and try to like measure where all the things are and then decompose it and understand all this. And really what you find is that it is a liquid. It has a density function that looks like liquid. It has dynamics. The ants are moving around relative to each other. And so this thing is forming a liquid of ants. You can look sort of at the edge of one of these they're all moving around a little bit. The ones on the bottom are interacting with the water and causing the buoyancy, causing them to float up and down. Okay, but they don't get to breathe as much. So the whole thing has to kind of recycle, and the ants have to move around within this liquid. Okay, now, when you look at the raft of ants on the surface, if it was really a ball, it could sink too much, and that could be dangerous. Really, this raft wants to spread out onto the surface of the water. And that looks a lot like this oil thing we talked about. So what if we do this experiment? I'm going to take a droplet, actually not me, David. I don't like to work with fire ants, but David is going to take a droplet of fire ants liquid, so a group of fire ants, and put it onto water. So on the top, we have the top view. On the bottom, we have the side view, as you'll see. He's going to put this ball there, and you will see it goes and it wets the surface and spreads out, I think in the end, to a 2 ant thickness thing. Yeah, correct. It's, you know. All right, so we have what looks like a liquid of ants. It looks like it wets water and has this liquid phase separation property, just like we had oil and water. Now, does it really flow? Well, we can do some experiments, and here's where we're going to get something. It's not quite like peanut butter, but it's a more what we would call a complex material. So if you just watch one of these things, you can watch them change position, right? So if you stare at one ant, it will not stay in one place. It will end up moving throughout this raft here. Okay, but then we can take a ball and we can squish it, and this is going to be more like silly putty. So if you squish it on a fast time scale, which is not very fast here, it acts like a solid, right? If you take the ball of silly putty, it will bounce if you throw it hard. If you take the ball of silly putty and you slowly squish it or stretch it, it just stretches, right? It has to do with the speed at which you are forcing or deforming this material. And that's the essence of what a complex material is. It has like time scales that change its behavior depending on how fast or slow you're doing this. If you've ever played with like cornstarch and water mixtures that people call oobleck, same kind of thing. Peanut butter is related. Afterwards, we can talk about it. Peanut butter is cool. Ketchup is super cool. How do you get the ketchup to pour out of the bottle? I mean, now they have plastic things. Now they have plastic things, and that's cheating. But when they had the glass bottles of ketchup, what did you do to make it pour? Yeah, that's a good way. So here's something you do next time. You want to make sure it's not full, like half full. If you shake it up first, it will pour. If you don't shake it up, it doesn't pour. So the people in the restaurants who used to fill your ketchup bottles up to make it look really pretty were doing you a big disservice, because you would never be able to, okay, so you had to stick the thing. You stick the knife in, and it's full of ketchup, and that's no fun. Okay, great. So we have this viscoelastic material. Okay, and you know, one thing you might say, does it really flow? So if I had a ball falling in a fluid, or here I have the fluid kind of going upwards around this sphere, right? The fluid particles go up and they hug around this. And you know, what happens on the other side is very interesting, and it depends on how fast things are going. If this was going really fast, you'd get all this crazy stuff happening in the back, but we won't. We will have it. Biology tends not to have that. But okay, so if I take these ants, and then I stick a penny, which is like a ball, and I let it go for a while, you can see that it sinks, and the material, the liquid of ants, flows around it, just like here. Okay, so this ant liquid is really a liquid. Okay, and these collective things have made it liquid, but this liquid does something Terminator-like, not really Terminator-like, but cooler than a normal oil would do on top of water. So here we can watch one of these nice rafts. This is looking from underneath. It's from the BBC. You know, they make really beautiful, beautiful things. And you know, here this is a pretty big raft, as you'll see when they zoom out. This is like this thing is just floating along in this flooded rivery thing, and that's fine. Okay, and what we're going to see, good eye, is this thing is going to be expanding, but not uniformly. The thing is going to start making like tubules or extensions that are going in one particular direction. It's making a flow spontaneously in one direction and not the other direction. Oil does not do this in your salad dressing. Decide to go left. right? That does not happen. Okay, but this one does. Those are actually baby or eggs. Yeah, there's a lot of ant biology we could talk about. We're not gonna talk. So, in normal fluids, like here you have the legs of wine or the tears of wine, however you want to talk about it. Physicists like to do this because they like wine. There are these like little tubules that can come out, but those are all coming out kind of uniformly. There's a cool story about the pattern of them, but we don't have to worry about that. But this is very different, right? These are forming this coherent thing, and they're doing it because they want to get to dry land. Okay, so this is a fluid that decided to make one of these, what we would call a viscous finger, is actually or a Taylor finger, the fluid dynamics term. But they realized that there was something to go to, and they spontaneously made a flow to that, and now they can offload onto the land and make, a new colony, new happy colony. Okay, so this is not only are the fluid properties important, so they can stay afloat by phase separating from the water, but this activity, the ability to move the fluid and flow it to a particular place, is a particularly not, active thing to do, and your oil would never do that. So you may have seen ant mounds that look like this. This sometimes also happens, sometimes on land, sometimes on the water. Okay, and they form these towers, okay, by trying to move up. And it turns out if you mathematically look at the shape of this tower, it is the same as the Eiffel Tower. The ant hill is designed so that every bit of ant hill has the same amount of pressure on it. Okay, just like the Eiffel Tower. But unlike the Eiffel Tower, this is not a solid. This is made of a liquid. And in fact, you can do X-ray. So this picture here is from X-ray imaging. You take an anthill with all the ants going, and you shine an X-ray inside of it, and you can watch the ants do. And what you see is there's all these flows going on. And the way that they build these is not like we build things. How do we build things? Somebody draws a plan, and the surveyors come and they do all this stuff. And it's like from the outside in, right? The ants do not know about the design of the Eiffel Tower, or even how tall the tower is, I don't think, or how wide the tower is, or even where they are in the tower. So this is the self-assembly of an Eiffel Tower. How do they do it? What happens is they just keep going up, and if the force is too big, they fall down. And this happens until basically every ant is at the same force. And the shape that gives is the Eiffel Tower. Yes? So I would say this is partly not known. Partly they don't have to. Ants do a lot of communication. I'm going to show you a system in a second where they don't communicate at all. They communicate through physics. Ants communicate a lot with each other in many different ways. So like how they decide all to flow in that direction, I don't know. I'm not sure anyone knows, actually. That's a great question. You should come work with us. Okay, very good. All right, okay. So that's the answer. Yes, one more. Good. Yes. By very large amount. Yeah. Okay. Let's move on to the second thing. So this is my favorite cell. I've been working on this for many decades. It is called Myxococcus xanthus. This is a single-celled bacterium. So it looks like a snake, but it's like really small. It's a bacterium. It lives in the soil. It lives in basically every soil pile of dirt on the planet, kind of a thing. Okay, but it does not live it's cute as an individual, but it does not live as an individual. It lives in giant groups of like millions of cells. So this is a macroscopic centimeter-sized colony of that cell I just showed you. And next to it is an even larger colony of a different kind of cell. And the cell that I like so much, while it does nothing mean to humans, like you could eat a bunch of it, it would be fine. It kills lots of other bacteria. That's sort of its job. It's how it does things. Okay, and so what it's going to do is it's going to spread out and swarm and decide to kill all of those cells and eat them. I mean, it kills them by making antibiotics. They explode and then it absorbs their stuff, and that's how it eats. Okay, so you can see what happens as it's killing those things. It actually forms these linear looking things. Those are surface waves, like ocean waves. Okay, so I have a thick layer of the moving cells. They form a fluid, not surprisingly, as we've been talking about. And on top of that, I basically get surface waves. Okay, those surface waves, we think, allow the cells to mix and get sort of everybody gets to eat. kind of a thing. On the left, yes, the left, very good. Those cells were unlucky and did not find any of the prey that they were going to eat. And so about 100,000 of them all got together. And whereas in the beginning, this fluid was wetted on the surface, they de-wet to form droplets. So that is essentially a solid droplet that you could find in most piles of dirt that has 100,000 or so of these Myxococcus xanthus. There's spores inside of this, which is an extra step of coolness. We don't want to talk about that at this point. But what they've basically done is they've gone from a fluid that liked to be on the surface to a fluid that de-wets into droplets. So if you had a raincoat and you wanted to do this, you would have to change the properties of the material of the raincoat. What we now have is a liquid, not made of water, but made of cells, that can decide for itself whether it would like to spread out on the thing or form these little droplets. Okay, that is pretty cool. Okay, it's a material that can make decisions and undergo these phase transitions on itself. So if you watch what happens when this happens, you're going to see these droplets are forming. In the middle, what you see are these layers of this fluid. And so this fluid is it's not kind of a normal fluid. It's basically a two-dimensional fluid that stacks on top of each other. And if you zoom in even more, so here's a collection of this at the very beginning. You see there are little holes in this 2D layer of fluid. And then you see all the little cells, little lines. Okay, but you know, this is not what it looks like. This is what it looks like. They're always moving around. And so this is a liquid, right? Like my neighbors are changing all the time. I'm moving around. I stay as a cohesive whole. So it's not a gas. It's not just flying apart. It's really compact. Okay. Yeah, these are guys real slow. We do have other species that this would almost be real time. But you know, being slow has its advantages. Like it's easy to take movies of them. Okay, so this is a special kind of a liquid because it's a liquid made of rod-like molecules. Okay, and when I take rod-like molecules, they tend to want to line up with each other. This happens in the macroscopic world too. If you take your box of matches, you guys are all old enough to be allowed to have matches now, and you dump them on a table and you kind of smush them together, a whole bunch of them will kind of line up like this because it's easier to pack them like this than all random ways, right? Kind of thing. Okay, so this forms something we call a liquid crystal because there's some order, like crystalline order, except it's a liquid. Okay, and you know about liquid crystal. Okay, liquid crystals, like this display, are made of fluids that are from rod-like molecules that like to line up. And the ones you use in a watch or in the projector are molecules that interact with light. And you change this orientation pattern so that it can like block light or not block light and allows you to turn on like the pixels of the watch. Okay, same kind of thing, except now instead of little molecules, we're talking about cells. So what we want to do is we want to look at the orientation of all the cells. So I took this same movie here, and now I can just tell you which way that they're pointing, not having to look at each individual cell. And you can see that mostly the pointing is kind of static, except there are these funny locations where like it was pointing here, but now it's pointing there. And in fact, there are specific points in space where it seems like near it, there's all the orientations represented. And these are called topological defects. They happen in all of these things. So you can go home, put all your matchsticks together, make them all perfectly ordered, and start just taking a few of them and rotate them. And what you will generate are patterns that look like this. You'll have triangle-looking things and comet-looking things. And someone actually had a fingerprint with one of these. We found it on Google. And I was like, oh, that's really cool. Okay. And so these things come in pairs, and there's a whole really interesting physics of how this works. And you can track where these go. And what you see is these topological defects are where you form layers and holes. Okay, so all the action is at these locations of these topological defects. And so we can take the sort of all the physics that we understand from liquid crystals, but now we have this activity, right? These molecules drive themselves in one direction along their length. That's not something normal liquid crystals do. And so in fact, we get different physics for these active liquid crystals. And that physics is what explains how you build these kinds of systems, or how you build these different layers. Okay, so in the lab, we can take these things and we can stick them down in regimes in which the cells don't interact with each other too much and basically nothing interesting happens. And then we put down the cells in a regime in which they go really, really fast. They strongly interact with each other. They try to go as straight as possible. And what happens is the system all of a sudden makes these droplets all at once everywhere. Okay, so we can take a fluid and do this. I mean, I can do this with water too, right? Like I could put it on one surface, another surface, and like this. Okay, but the cool thing is that when we ask what the cells do when they form these droplets on their own, when they're starving, they change their own behavior and their own interactions to go from a fluid that wants to be wetted to a fluid that wants to form droplets. What was that? That was really weird. I'm going over here. Yes. No. What changes is the behavior of the cells. So this is an example where we think there is no communication between the cells except bumping into each other. And that's all you need. But evolution found that if, when I'm starving, I go from like to as fast as I can go, my population will do this. There was more survival. And so that behavior was programmed then in through evolution. Okay. But there's no communication between the cells, all mechanical. Yes, sir. So we're going to look at birds in just a second. And it is true that, well, yeah. The birds can't bump into each other in the flock because they will fall down. And there's a big penalty, okay? So birds try to stay like kind of the right distance from each other. And what we're going to see is they like to go in the same direction because then you don't bump into. Okay, so it is true that, like, so that's through like vision. I see where you are. I see where you are going. In fact, I look at all the birds around me and I average it and I kind of go that way. Okay. So that's not a mechanical bumping, but it's not a communication where I'm like, hey, which way are you going? You're like, well, I'm going that way. Okay, let's all go this way. Something like that. That would be a different level of communication, which birds could do. But in the flock, as far as we can tell, they basically use vision to try to align their cells, which is much more of a mechanical sort of. In the birds? Oh. Yeah. So we've done a lot of work to try to look if there's signals being sort of dispersed or signals being passed to each other from cell-cell contact. There's a lot of genetics and things that we've done behind all of this. The other thing I would say is we have species that are self-propelled rods that do not live in groups. But when we put them in our experiments, we can make them do that. And they definitely don't have this communication because they didn't evolve to do anything interesting. So there may be some communication about the decision to do this, right? Not, oh, let's all go over there, but when did you eat? Yeah, when did you eat? Did you? There's some joke there, and so that may be there. We haven't ruled out in some way, but as far as we can tell, like the mechanism via which this happens does not involve communication. Other microbes do this. So there's some slime molds will make interesting patterns. You may have some in your house, and those there's an interesting chemical communication they use basically to make a global map. And then each individual cell reads the map. And so that's a communication-based kind of collective. There's a question. No? Yeah. So in Dictyostelium and Discoideum, what you do is we all release a chemical, but your releasing that chemical depends on what you've sensed from that chemical. And there's this a circuit, genetic chemical circuit, that basically makes it want to oscillate. And so what happens is we all start oscillating, but with a phase relationship that has to do with our distances. Whoever started this thing first basically wins and becomes the center, and that makes sort of a map that you can. Okay, the last story, which will be pretty quick, I want to talk about is about bird flocks. This is about European starlings. This is done work in Rome by two colleagues of mine. And why do birds form flocks? I think there's lots of reasons, but one of the reasons is because there are these predators, and the predators would like to eat the birds. And so part of it is strength in numbers. So a lot of herding animals, there's just strength in numbers. You know, if you're all together, one of you may get hit, but maybe not you. That's fine. But there's going to be more to this story. So over the Basilica in Rome, there's essentially a starling flock every day. Over lots of Rome, there's a starling flock, but there's one there. And if you go on top of this museum and set up 2 cameras in a stereoscopic setup, so you have 2 eyes and you can see in 3 dimensions because you have 2 cameras that are tilted at an angle. So if I take 2 cameras to an angle, I can make a 3D image of the flock, and that's exactly what they did. They went to the top of that museum, they set up these 2 cameras, and so this is one flock viewed from slightly different angles. You can then triangulate, figure out which bird is which one in each of these images over time. So with a movie, and you have a 3-dimensional representation of what the flock does. Okay. And then you can look, for example, at how the flock moves over time. So this is the speed of all the birds inside of the flock. The flock is moving. That's all good. Okay. So now what I'm going to do is I'm going to subtract the mean motion of the flock. So the whole flock is moving like this, and I subtract that motion from the bird. So I'm sort of looking at what happens if I sit in the middle of the flock and I'm moving with the flock, and I look at what all the other birds do, and I can see these other things, right? Some of the flock is moving this way relative to me, and some is moving that way. And I look at how these are related to each other. And what I learn when I do this carefully, mathematically and statistically, is that the bird on the far end of the flock knows exactly what the bird on the other end of the flock is doing. Instantaneously. Okay. Now, you may say, well, like, well, okay, I mean, like, I'm following you and you're following her and she's following him. And so sure, that would be different. That is akin to sound. You are hearing me now because I am pushing on some molecules and they are pushing on some air molecules and they're pushing this way. And eventually it pushes on the eardrum inside of your ear. But that takes time. That takes the speed of sound to propagate. This is different. This is not that bird over here wiggles and there's wiggling, and then this one over here wiggles. This is that as this one wiggles too. They are connected in ways that aren't having to do with sound. The whole thing is essentially one connected object. That's what you could think of as kind of ultra sensitive. And so this means that when I have this flock flying around, you can see some of the predators. When they come, the whole flock can respond much quicker than if the hawk came here and you moved and then you moved and then you moved and then you moved. That would be slower. Yep. Correct. It's like they're a solid. So a solid does this because the speed of sound, no, but the solid does it because the speed of sound in solid is very fast. It's still the same, right? Like if I push on this end moves, but actually there was a wave that kind of did that. It just was very, very fast. This is different because it's not a solid, but it behaves that way in some sense. Okay. So yeah. Okay. All right, so I'm going to end there. I hope I've convinced you that collectives of living organisms can form these active materials that extend the phenomenon of what we normally think about in terms of conventional matter and conventional physics. And I think there is a hope that by harnessing some of these concepts that we can someday build smart and active materials that can do interesting and useful things for us. This is a dream at this point. I mean, the people work on this, but something practical is not there. And I suggest that we would like to not build